Okay, so we're going to go over the second law of thermodynamics. The second law of thermodynamics is the one that explains why when you put a hot and cold object, the hot object gets colder, the cold object gets hotter, and not the other way around. Because if it went the other way around, if your coffee that you put on the table got hotter and the table got colder, as long as the energy transfer from the cold object to the hot object, like if the cold object lost 20 kilojoules and the hot object gained 20 kilojoules, as long as that was the same, then the first law is obeyed. There is nothing in the first law that says that the hot object must lose heat and the cold one must absorb it. It's the second law that explains that, and it has to do with probability. So when you put a hot object and a cold object next to each other, the chances of a molecule in the cold object moving slow and a molecule with a hot object moving fast, the chances of that collision, where the energy is transferred from the hot object to the cold object, because this is moving slower, this is moving faster, so it transfers the energy from the hot to the cold, will be higher than the other way around. And that's why generally what happens is the hot object loses heat and the cold one gains it. So the second law of thermodynamics says the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So any process that is spontaneous has the higher chances of taking place. That's why it happens. Just like every time you buy a lotto ticket you lose, it's because the probability of losing is much higher than winning. And so that's pretty much probability at work. Every time your car, after you clean it, gets messy after a month, or your room, same thing, again has to do with entropy. The probability of it getting unorganized and messy is much higher than it remaining organized, so therefore it gets unorganized. So anyways, that's how we show that. And delta S universe is equal to delta S system plus delta S surrounding. Again, system is the part of the universe that we're interested in, surroundings is anything outside of that. And so now let's go over calculating entropy changes in a system, like a chemical reaction. So if you have a chemical reaction and you want to calculate the change in entropy of that, it's very similar to change in enthalpy. So it would be the sum of the entropy of products minus the sum of entropy of reactants. That hollow circle means under standard states. Standard states, again, is when you have both reactants and products present. If the reactants are aqueous, their concentrations should be 1 molar. If the products or reactants are aqueous. If the products or reactants are gaseous, their partial pressures should be 1 atmosphere. And if they're solid or liquid, they must be pure. And generally temperature is 25 degrees Celsius. Now we can make some generalizations due to gases having much higher entropy than solids and liquids. If since gases have much higher entropy, and to calculate the change in entropy of a reaction, we take product minus reactant. If a reaction produces more gaseous products than it consumes, then the delta S for that reaction will be positive, because this value will be bigger than this, so this minus that will be positive. And that's similar to, for example, taking papers out of files in your room, or clothing out of the your dresser and basically out of the closet, and basically spreading them out all over the room. Because gases have much higher entropy. When you make gases, you're increasing the entropy a lot, so the delta S is positive. If you produce less gas molecules than you consume, then delta S is negative. It's like taking all those papers, putting them into files, and organizing things. So how do we put this knowledge to work? Well, let's say that we have these 3 reactions and we want to arrange them in terms of increasing entropy change. So if you look at the first reaction, the delta N, change in the number of gaseous molecules, would be 1 minus 2. So that would be negative 1. So in this case, we are organizing things. Delta S will be negative. Here it would be 4 minus 2, so it's plus 2. So in here we're unorganizing things, so the delta S will be positive. And in here would be 2 minus 4. So it would be minus 2. So again, we're unorganizing things. So in terms of increasing entropy, the one that has the highest entropy would be reaction number 2. Then it would be 1 if we're doing relative. And then the third one would be the most negative. So this would be increasing delta S value. So you get questions like that where you need to figure out, without doing any calculations, whether the delta S for the reaction is positive or negative, which reaction has a bigger positive delta S than which, or less negative than which, and that's how you do it. And then to actually calculate it out, let's say for this reaction, calcium carbonate decomposing into calcium oxide and carbon dioxide, it's not an equilibrium. So I'm writing it this way, and so in here, again, we take products minus reactants, so 1 mole of calcium oxide, its entropy is 39.8 because it's solid, so its entropy is low. Carbon dioxide is a gas, its entropy is much higher. So I take the coefficients, I have 1 mole of this, 1 mole of this. So remember, everything in chemistry is per mole. So if I have 1 mole, I multiply by 1. If there was a 5 here, then I would multiply this by 5. And then for so these are products minus reactant. Reactant is calcium carbonate 92.8. Where do I get these values? These are all from a table that you will be given during exams and quizzes, from a table. So those are the standard entropy values for those substances, and then you can look up in a table, just like the enthalpy values that you look up in a table, so they're similar. So then this value comes out as 160.5, it's positive, and we could tell it was positive because we're producing 1 mole of gas, so it's 1 minus 0, so it's plus 1, so the entropy should be positive, and it is 160.5 joules per Kelvin. Why is it joules per Kelvin? We're gonna learn in the next video. We're gonna go over how you can calculate the change in entropy of the surrounding as a result of what happens in this system. But we'll do that in the next video.